Welcome to the GOTO Podcast. In this episode, you'll discover the amazing world of graph databases and how you can leverage graphs to understand your data with Jim Weber, co-author of Graph Databases, and Nicki Watt, CTO at OpenCredo. Created for developers by developers, GOTO gathers the best minds in the software community. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in Chicago, Amsterdam, and Copenhagen, and by subscribing to the GOTO Conferences YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Welcome, Jim. Good to see you again.
Hello, Nicki. It's lovely to chat with you. It's been a while.
It has been a while indeed. And we're talking about your wonderful book, Graph Databases.
Yeah, and it's really apt that it's the two of us, right? Because I was thinking about this before our chat, and actually the first version of this book I wrote with Ian Robinson in the kitchen of your old office about kind of 9 or 10 years ago.
Wow.
So we've got some history here, right? I mean, thankfully, we're talking about the updated version or the second edition this time around. But it's a lovely thing that we have that shared history that we used to clog up your tea room with our writing and rambling.
Yeah, we enjoyed it immensely because we got to actually ask you all the difficult questions as well. So it was really good. It was really good.
Fun times.
Excellent. Well, let's kick off. And I think a really good sort of maybe just introductory sort of question. Let's start with something simple. What is a graph and what is a graph database?
Yeah, so it turns out that that's still a common question. But in short, a graph is a data model. It comes from maths, but you don't have to be worried about it. You don't have to get all mathematical about it. But most software people find it very straightforward. A graph is a model where we have nodes connected via relationships to other nodes. And because we're software folks, it's pretty simple to understand. We've got circles that represent typically entities, and we have relationships between those circles. So if you can draw a circle and an arrow and another circle, you already understand graphs. So for example, the kind of graphs that everyone is familiar with, things like social graphs, I could say that I have a node that represents me as Jim, and I could have an arrow representing follows. I could label that arrow as follows. I could have a node representing you, Nicki, and then the graph would be Jim follows Nicki. So actually, it's a really simple model. You're not constrained by tables or kind of insane normal forms and joins and all that stuff. It's very much more like an object or domain model as we think about it. And if we take those simple idioms of nodes and relationships, then we can build really big, sophisticated, high-fidelity models. And then if you're into it, there's also a bunch of maths and ML and other stuff you can apply to it. But if you're just like a normal human software developer, then you can just build really big, high-fidelity models and ask questions of it and get answers. So I could ask, for example, who do I follow? Or indeed, just as cheaply, who follows me? Which is kind of an expensive thing to ask with, for example, in relational technology.
So you've explained that graph databases are really good for the sort of highly specialized sort of connected data, and using the sort of social network as an example is great. But not everybody's building, sort of social networks out there. That's always the classic example, I think, that people kind of use. So like practically, what are the other kind of maybe sort of common use cases that people would actually use graphs for that are not in the standard sort of social network land?
Yeah, so it turns out that when I was clogging up your tea room back in the day, we always used to kind of say social because it was the thing that people understood. But it turns out that graphs are reasonably horizontal, right? In the same way that relational is reasonably horizontal, or probably documents are reasonably horizontal. And what we found over the years is that graph models are natural for quite a broad array of use cases. Actually, my first graph use case was retail recommendations. So looking at your purchase history and looking at what would complement your purchase history and then recommending it to you. That's what got me into graphs. That's what pulled me into this whole domain. But equally, I remember some of your team working on oil and gas pipeline optimization. So of course it's a graph problem when you think about it for a moment, because the pipelines are a network. And then of course, if you say, oh, network, well then it's IT, it's ops, it's telecoms. But then actually our lives are very connected. Your healthcare history is a graph. It's a It's a graph of interventions and clinicians and hospitals and prescriptions and all that kind of stuff going on. And then so is things like bill of materials. It's a complex graph of all the widgets I need to create an aeroplane or a laptop or a car. And so what we're finding now that is that, although it's very easy for us to talk about graphs in the familiar sense, Facebook, Twitter, that kind of thing, that a lot of the times problems that we would solve creatively with relational databases are very humanely solved with graphs. Again, it just comes back to that circle, stick, circle idiom. And any idiot can do that. And I know because I am one of those idiots. So if I can do it, like anyone else can feel profoundly powerful with graph tech.
That's great. That's great. So, I mean, could you maybe talk about what graphs are not good for? So, I think we're probably quite biased in terms of we think graphs are good for everything, but there are cases where they're not maybe a good fit. So could you maybe speak about what those are?
Yeah, absolutely. So I think if you've got just a bulk data storage problem, you want to store your web server logs, you want to build a counter for votes on Britain's Got Talent, something like that. There are better databases out there, right, for doing that kind of undifferentiated bulk storage. And, everyone knows them, right? You want to build a counter for Britain's Got Talent votes, use Cassandra. It's great for that. Yeah, you want to continue to run your legacy payroll system? Well, you've already got Oracle. Carry on doing Oracle because it's square, uniform data. It's not going to cause you any bother. But what we're observing is that when you want to do the kind of higher value stuff, where I don't just want to analyse the kind of aggregate votes for an act on Britain's Got Talent, but I want to understand the social demographics and the way that people are voting, which of course in the real world does manifest itself, right? We have an important election coming up in the US, for example. So understanding sentiment, that's when you get back into graphs, because graphs are a really useful analytical tool for that kind of stuff, which is more important or more valuable, I think, than just the aggregate numbers. So it really is if you've got something that's a bulk storage problem, kind of web server logs, all that stuff, go find your data lake, dig out your Hadoop, deploy your Cassandra. These are wonderful pieces of kit. But where you want to know where you want to bring the analytical stuff to bear, then a graph would still be a good fit for that stuff. And in fact, what we often see, because graphs sadly don't rule the whole world yet.
Not yet.
We see these things playing together, right? So you'll see that, for example, if I've got petabytes of storage about NASA mission data or something, there's not a lot of value in having that all graphed, but there is a lot of value in having a graph window on top of that to kind of bring the kind of analytical techniques that graphs provide onto a window of that data that's of particular interest. So we see those things playing together nicely all the time now, which is very pleasing. Interesting
enough, one of the things I was recently looking at was actually the FinCEN file revelations that came out. And this is where the ICIJ, which is the International Consortium of International Journalists, actually used graph technology to reveal the role of global banks in industrial money laundering, which is a fantastic way of seeing who's doing what where or who's doing the wrong things where. So could you maybe speak a little bit about that and actually explain how did graphs there help to actually blow the lid on this whole story?
Yeah, so I mean, the ICIJ are pretty busy people, right? So they've done a few things like this, I guess most famously Panama Papers with that huge data leak from South America. Which, by the way, caught the Prime Minister of Iceland. It also caught former British Prime Minister David Cameron's father in having completely, I'm sure, above board offshore accounts for perfectly good reasons, like he lives in an oppressive regime, something like that. So the value of graphs here is that they're a really good structure for understanding flows of money. So the ICIJ, when they did the FinCEN stuff, so this is the United States Financial Crimes Enforcement Network, that's the acronym. And the idea is that any financial institution, when it has a suspected dodgy transaction, it has to report it. Right, so hey, I think this is iffy in some way. And so what happened was about somewhere order of magnitude of 3,000 files were dumped of what's called SAR files, suspicious activity report files, representing around 2 trillion with a T, $2 trillion worth of suspicious money movements. And it turns out that many banks are either victims or unwittingly allowing suspicious money to flow through their networks. And it's really hard to see, right? You've worked in banking, I've worked in banking. The systems there are huge, they're complicated, they're voluminous, and they're interconnected in a myriad of different ways. Compliance is a nightmare, right? Because you just can't see the wood for the trees. So what the ICIJ did, they got these documents. They said, well, look, this is a terribly difficult problem. Let's have a look at how each of these documents, how each of these suspicious activities relates to, payee and payment and payee and that kind of thing. And when you connect these things together, circle, arrow, circle, you see it starts to form a graph. And that graph represents flows of money from institutions through the banks through to other institutions. And then using that, it's actually very straightforward to start asking questions about, what is this particular flowing through this major US bank from dodgy company to dodgy company with seemingly no useful economic activity? And those are the kind of questions that a graph database can easily answer, because you're just pattern matching. You're drawing pictures, at least in Neo4j using the Cypher query language, you're drawing pictures of patterns that you're interested in. And those patterns are learned by domain experts or even can be learned by algorithms nowadays. And then you say, hey, database, find me these kind of suspicious patterns in this graph, in this network, and tell me about them. And so the ICIJ are pretty good at this now. They've done it for several large newsworthy items where they pour their data into a graph and they understand the flows of money in this case, or they've understood the hierarchical and opaque ownership of trusts and offshore accounts in other cases. And they're able to shine light on that by letting the database do the heavy lifting. We understand that a single human couldn't hold all of that complexity in their minds, but by just asking the database to, hey, do the heavy lifting, find me the suspicious stuff and show me who it's coming from, who it's flowing through, because they're probably in trouble, and where it's going to, and then we can get a lot of value from that. And by the way, sitting here as we are in London, I will point out that 3,000 British companies appear in these files, and it turns out that's more than any other country. So I guess we won something, right? We are the champions. Yay, go Britain. So hopefully now, what I'd really hope, all joking aside, is, the ICIJ keeps setting this trend. They go into a particular, typically, compliance area of finance, and they shine light. What actually could happen is that the institutions involved could take that tech, because clearly the big finance companies have a brilliant array of technologists working for them. So they could take those techniques and simply in-house them, so they didn't have to have the journalists, kind of doing it after the fact and causing embarrassment. So if any of you folks out there in finance and you want to do this stuff, look at what the ICIJ are doing and copy it in-house, and it will save you a lot of trouble. When
I was looking at those articles, it did mention graph data science in there. So you've spoken just about, so there's graph theory. And actually, I think in your book, there's a whole chapter on predictive analysis with graph theory. So, I mean, how important is it for people to really understand and the sort of the fundamentals of sort of graph theory and data science in order to actually gain insight into some of these type of things? And maybe you could talk a little bit about what graph data science actually is, because I get some questions a few times from sort of clients where it's like, well, I'm already doing data science, so how is this different? How is graph data science going to help me?
Yeah, it's quite a lot to unpack there, right? So at the most normal level, you don't need to understand graph theory to take advantage of graph databases, because they look just like normal domain models that you're persisting. And in fact, the origins of Neo4j, when Emil, my boss, built it, he had this idea that it was going to be a persistence mechanism for your Java domain model, right? It's kind of like the Smalltalk runtime. So if you're a normal software engineer, I beg to differ, but we're not meant to be having a fight about programming.
It just didn't make it.
But I came to Neo4j not as a graph theoretician or a data scientist or anything that grand, but just as a software nerd. And I just felt that the way that I perceived a database should work happened to be how graphs did work. So I have stuff that's connected to other stuff, and some of it's densely connected, some of it's sparsely connected, and the relationships go in both directions and they have names. This is always, it's kind of like the ERD that we draw if we were going to use relational, right? But then you didn't have to go into the relational model. You were left at the kind of ERD level, which is a lovely graph. So you don't have to care about this. But then once I got into graphs, I kind of found that was the gateway drug. And it's like, oh, there's like 300 years of like research here called graph theory, which is, everyone kind of knows the terms. But it's kind of amazing, right? It's like a really active part of mathematics, has been for years. And I think it forms one pillar of, if you like, the data science part of graph data science. And it's an analytic tradition that comes from maths. So in the book, we wrote about link prediction. So the easiest one, again, I'll fall back to a social graph because it's the one we all know. Like if I'm your friend and you're a friend of Russ, then at some point I'm going to be a friend of Russ because you've effectively transitively expressed trust or good judgment. Or in this particular case, I have to say bad judgment because Russ and I are both cowboys. So what graph theory will allow us to do with this notion of triadic closure is predict where relationships will appear in graph or should appear, and equally where they shouldn't appear. So if you hate me and you hate Russ, then it makes sense for Russ and I to become friends so that we could double hate you back. Right, so there's all this kind of richness in graph theory, and we could do a bunch of other algorithms, like we can find cliques. You could tell me the hierarchical chart, the organization chart of OpenCredo, which is, I'm sure, a perfect tree. And then I could take your email server and analyze it. And I'd find the graph in that tree, because it will be, because you communicate with each other across layers and so on. But then I could find things like the cliques in that. So if actually, who likes working together? Who is the most important? Obviously, I think should be the CTO that's the most important, but it may well be that there's some other member of staff on your team that has incredibly high centrality or incredibly high page rank, right? So that loads of information flows through them and you hadn't realized it because the org chart doesn't make it apparent. So we've got all of these analytical tools that the mathematical boffins have already figured out to figure out, popular nodes, to figure out neighborhoods in our networks and so on. And what's nice about, modern graph databases is you don't need to understand the internals of those. You can just say, oi, database, tell me who's popular, or tell me which node is popular. Oi, database, tell me which nodes are similar. Oi, database, tell me about the cliques in this graph, the neighborhoods in this graph, that kind of thing. And so that comes for free now, modulo processing time. But that's the analytical tradition. And I was a huge fan of that because I got to tell you, it blew me away, right? When I discovered this stuff, it was like magic to me. Like, as I guess for many software people, maths does seem magical. But then more recently, there's these kind of whippersnappers coming out of the data science and machine learning community, and they're like, move over, granddad, we've got new stuff. And so what they're doing is they're saying, look, we've got this graph and the graph is wonderful. And often what we want to do is feature engineering over data to be able to build good models. But what the graph provides is more features. For example, in a document database, if we represented you and I as documents, we may well be able to extract features, like age, profession, place of birth, where you live, that kind of stuff, right? And you might be able to build a model that predicts something useful. But also imagine now that you had our position in the graph, right? So now you can start to reason about my connections, about my centrality, about my page rank. All of these things can become additional features. And what the graph data science folks are doing, in a nutshell, is trying to figure out how to take those really useful graph features and extract them in a way that preserves the properties of the graph, but still feed them into their machine learning pipeline. So it turns out you can mix the analytical tradition and the kind of ML tradition, if such a thing can be said. So I'll be able to take things like, hey, I'm really interested not just in Nicki, but I'm interested also about, her page rank and her cohort's page rank, or their centrality, or the clique that they're in, the neighborhood that they're in. And those will become useful features that end up going into my ML pipeline. They become part of a vector that I'm going to process. And in fact, the most kind of leading edge stuff that we're doing now are things like node embeddings, where we'll take a whole node and we'll preserve that node's locality as a feature as we embed it into a vector for subsequent machine learning. So I think you've got these kind of two complementary things at play now, the kind of old school graph theory analytics, and I mean old school in a reverent way, not in a kind of disparaging way. And you've got this new cool stuff around ML, and it turns out they fit together. And look, we're not like the leaders in this. We're just fast followers. The leaders in this are the likes of Google, the University of Edinburgh, the kind of big brains in this area. And so they're leading the charge with GraphML, and we're following as fast as we can and trying to provide a kind of packaged version of that technology for normal folks like us.
Great. Yeah, I think one of the things we've also found is that sometimes you have things like you can have NLP and those type of things which precede the graph. So we found, for example, if you've got unstructured data, you can run NLP over that, do entity recognition, and then actually put that into the graph and then do the analysis from there. So yeah, as you say, you can do it sort of afterwards, during, and before as well is a good pattern.
In fact, that's how, as I understand it, that's how things like Amazon Alexa and stuff work. They have exactly that kind of pattern. So even the stuff, the commodity stuff that we have around our houses is at some level graph powered in that way.
We've got these graphs and everything, and we've worked obviously on a few projects, and it's always important to actually pay attention to the model in the graph, because whilst you've got all these things connected to each other, you've got to be able to actually programmatically query it and do something with it. So what kind of pitfalls do you see people kind of making when they're getting started with modeling graphs and things like that?
Oh, Nicki, that's a really awful thing to ask me, because you know I've messed this up. So I'm good at telling you the pitfalls. So look, in graphs, you know this, we have this idiom like what you draw is what you store. It's a really nice idiom because it means if you can draw a domain model on a whiteboard, then that's the thing that you're going to persist in your graph database. So there's a real small semantic gap between your business stakeholders and the kind of bits and bytes on disk, which is overwhelmingly a wonderful thing. Like, if you compare that to relational, where you draw the domain model, the business stakeholder buys in, great, and then you've got this like cathedral, this wondrous thing on in Oracle, for example, and you need to be a real expert to be able to translate between the two, because the stakeholder looks at your Oracle model and they're like, So one of the nice things about graphs is what you draw is what you store idiom is great until it isn't. And I'll tell you why. English. Now, I happen to be English, and I'm functionally monolingual in English. And that means that sometimes I'm sloppy. And actually, we did honestly write this down in the Graph Databases book. But we were working on an email forensic system early on in Neo4j's days. So we had a customer that wanted to understand who's emailing who, looking for potential things like people leaking secrets, right? Which you can do with graph analysis. So it was clearly a very graphy problem. And so we did our detailed modeling, and we applied the idiom what you draw is what you store. So it was like, okay, well, Anne emailed Dan. So a node representing Anne, arrow representing emailed, and then a node representing Dan. That seems fine. And we also double checked it. So we also have this idea in graph modeling that if you can read a sentence and it sounds correct, then your model's probably correct. So let me try and read that. Anne emailed Dan. Well, that's perfect English, right? Obviously. So clearly the model is correct. What I've drawn is what I've stored. It's now on disk. Right, let's write some queries. Right then. So who was involved in an email that mentioned fraud? Just obviously fraudsters will write fraud in the title of their email. That query doesn't work. And why doesn't it work? It's because English. Obviously, I'm not going to blame myself. It's the language that's the problem, right? It's so easy in English to say Anne emailed Dan. And it's such a shorthand, but it's not true. It's not a true reflection of what's happened. So we missed some of the domain knowledge there. And actually what really happened was that Anne sent an email. An email is an entity. So Anne sent that email. And then that email was to Dan. It may have been CC'd Bill, right? But we missed out a key entity there because our use of English was sloppy. Anne emailed Dan sounded right, so we used it. And then when we put it out in long form, Anne sent an email to Dan and CC'd Bill is what we should have said. So it's really easy to kind of convince yourself that the model is correct by reading it and it sounding sensible when actually you've missed out some information from your model. You've got a lossy model. And I think that's one of the things that if you're new to graph databases or new to graph modeling, that's the thing that catches you out, because While there are many wonderful things about graph modeling, it's simple, it's pleasant, it's humane, it's expressive. You've done this, right? It is a joyous thing, and I'm always reluctant to go back to relational modeling after doing this. Relational modeling has rails, right? You're on your rails. You create your ERD, and then you've got a plethora of normal forms that you would choose to normalize to. We don't have that in graph world. So you have to be kind of on your toes a little bit so that you can realize that an email down is actually a terrible graph, and you've missed out entities, and therefore you've got a lossy model. So beware of that when you start your journey into graphs. I think that English, or whichever sloppy natural language you're speaking, can catch you out, and just double check that entities haven't fallen through the grates. In fact, we categorize this as, I verbed a noun, right? Because instead of having an email, I say, an emailed. And so look out for that verbing of nouns, because you may be missing out on important entities in your model. In fact, we do cover that in the book. And if you want to double down on my embarrassment as a terrible developer, then you can read that in the Graph Databases book as well. It's a warts and all story.
So for people that are starting out, the software world is changing so fast. It's so hard to sort of keep up. And your book was actually released in 2015, which was about 4 to 5 years ago. And whilst I do think, graphs are timeless, writing is not. So what's kind of changed since then? I mean, for people that are maybe picking up the book now, are there things that are still valid? Are there things that maybe they need to sort of be aware of in terms of stuff that's moved on?
Yeah, so I think you answer this question better than I could. I think the graph stuff is timeless. So the stuff in the book that's about modeling and so on, that's still perfectly valid. And there's other stuff in there that may be kind of good for introductory. I think if you're reading the book today, you should kind of read it with a slight filter on that. Some of the technical stuff has changed. So in the 2015 edition of Graph Databases, we talk about how you might extend the database using these things called unmanaged extensions. And that was because in that version of the database, we had a REST API that you could put plugins in and make it richer, make it more domain specific. And while those things still exist in Neo4j today, that's actually undergone quite a radical change. And now Neo4j has a binary RPC protocol called Bolt. And the Cypher query language itself can host procedures, which you can write. So almost we've taken the model and flipped it. Whereas it used to be expose your custom code as REST endpoints, effectively, as URIs that you can fire HTTP at. Now it's inside the database, and you call those custom procedures via Cypher. Cypher itself has matured. We wrote this against Cypher for Neo4j 2.0. And Cypher has just got better. So as we've had more experience with Cypher, there's a big team at Neo4j. About a third of the engineering team, one way or the other, are involved with the implementation and design of Cypher now. And so Cypher itself is just, we've knocked off some rough edges. It's become more, it's got more capacity. It can do more things. So when you see the Cypher examples in the book, and then you look at, say, for example, other better books, I'm sure, or the Neo4j documentation, you'll spot better ways of doing it, or you'll spot, hey, this didn't exist when Graph Databases was written. This is new and interesting. So look at that. I think that those are the things you should look at kind of as a developer. As an ops person, we changed the clustering in Neo4j. So when we wrote the book, Neo4j had a high availability clustering, but you were invited to kind of supply your own load balancing and stuff, which was fine for where we were. But of course, in 2020, that sounds a bit horrible, doesn't it? Even saying those words. So we changed the clustering model so that the database takes care of load balancing and stuff for you. And as a developer now, you simply take a driver in your chosen language, in Python or Java or one of the .NET languages or what have you. And then you see the database in an idiomatic way for yourself. You don't have to worry about, this is a cluster and I've got 3 machines in New Zealand and 2 in London and 3 in New York. All that stuff's taken care of for you. So there's a separation of concerns, which didn't exist quite so well in previous Neo4j. So in a way, it's simpler. But you're going to have to mix in your reading of the book with some reading from like the Neo4j website or something like that to get a more accurate picture, which as we you and I had a kind of a pre-meeting to talk about what we wanted to talk about, like a meta meeting, and you did tell me that it needed to be updated. I've taken that on board, talked to my folks at Neo4j, and we're kicking around the idea of a version 3 of this now, because I think you're right. You've embarrassed me into into writing again, and I hadn't thought that it was 2015 when this came out. In my mind, it was like, yeah, we did that book like a year or two ago, and it's still fine, and then we have this conversation. It's like, oh yeah, lots moved on actually. It's time for a refresh.
Excellent. Do you think one of the things you might cover in there? So you spoke about Cypher, but there's also GQL out there. So is Cypher still around, or is it dying, or is GQL replacing it? What's going on there?
So Cypher's still very active, right? There's still a whole bunch of engineers at Neo4j working on it, and actually outside of Neo4j, OpenCypher is taken up by other databases and platforms. So GQL is graph query language, and it's the graph analog of SQL, and it's being standardized by the same ISO committee that standardized SQL, which is nice. In fact, they are that committee. If my memory serves, they're called the Database Query Languages plural committee, which is funny because in history they've only ever done one language, and that was SQL. So now they finally earned their plural by looking at another language, and of course there's good reason for that. If we're old enough to have seen SQL evolve, right? And SQL has like subsumed every other competing tech that's come along. XML databases into SQL, kind of object databases into SQL. They've managed to kind of SQL has been kind of like the blob that's absorbed everything else. But ISO have decided that graphs are distinct enough to warrant their own query language. So they're building this thing called GQL, which I think is a helpfully unimaginative name, right? Graph query language. Fine, it's a query language for graphs. The main input to that is SQL. Is Cypher, man. SQL on the brain now, is Cypher. And I think the reason for that is, of all the people out there, including these huge database companies, Oracle, Amazon, what have you, we have the most experience, the most deployed footprint using Cypher. In fact, loads of people like Cypher. So it's one of the big driving forces in the design of GQL. And in fact, you can see the way GQL's going. It's a declarative pattern matching language, which sounds familiar because Cypher was the original declarative pattern matching language for graphs. So I think over the long term, over the medium term, GQL should be where it's at, in the same way that SQL's where it's at for relational. And a lot of that, the brain trust for that is coming from Cypher. And if you're on Cypher today, if you've read the book and you've done some Cypher queries, that learning is going to be valid, and you're going to have a really easy time moving on to GQL. My fervent hope is that GQL is just really good and everyone adopts it, because then I can move from graph database to graph database, and none of my knowledge is lost. At the moment, for example, 90% of what we see out there is Cypher. But then if you move into a new gig on a graph database that only supports like something legacy like Gremlin, then it's like, oh man, I have to relearn all this stuff. And I think hopefully GQL will level that playing field in the same way that SQL did for relational. So I think that's where it's heading. I understand there's a draft of the spec due out imminently. I don't know what imminent means for standards bodies. So I'm guessing, in the next year. So we'll have to see really how GQL looks for actual practitioners and get some feedback from normal, our data practitioners about where it's working and where some rough edges need to be hewn off.
Yeah. Jim, I have so many questions, but I'm sure we can't go on forever. So maybe let me finish with this. So you are a chief scientist. So what does that mean in terms of, what are you actually working on at the moment? What is the future of graphs and some of the sort of computer science angles that you're looking at?
Oh boy, I mean, there is, it feels like there's infinite computer science to be done in databases in general, right? It's a very CS discipline. The stuff that I'm particularly interested in is fault tolerance and scale for graphs. The model makes it interesting, right? So you could imagine a distributed graph database. There are some of those out there where you and I are nodes on different servers and there's a relationship between us. And the hardest thing now, which no consistency models directly address, is if Jim follows Nicki, then Nicki has to believe she is followed by Jim. And keeping the reciprocity, so making those things reciprocally consistent, is a real challenge. And none of the distributed databases out there do that today. They just take their chances. which is a worry because it means, there's a potential for a data race and a corruption. So I've been working with some folks at the University of Newcastle, up in the northeast, who we've been building consistency models that not just maintain the base acid semantics, but also maintain this reciprocal nature. So that if you delete that relationship, both sides agree that the relationship is deleted, and you don't get a non-deterministic query. If you query this side, you see a follower. If you query this side, no follower. I mean, that's just nuts, right? Because then you'll take that information and you'll use it to write other stuff into the graph, which will spread that corruption. So I've been working on that. It sounds really dull to most normal humans, but I'm a consistency model nerd, so this stuff's really good for me. But more broadly, I mean, across Neo4j, I think there's a lot of hard work going on in language design for GCore, and consequently things like query planning and optimization, which is a really hardcore piece of computer science. There's a bunch of stuff going on in down in the weeds, low level IO and bit twiddling, and understand how to get the most from modern computers. And there's just like a whole range of kind of very nerdy computer science stuff, right the way up to we have people who are doing R&D on how do you visualize this stuff? Because while you and I are quite used to ball, stick, ball, there are other folks for whom that's a completely meaningless visualization, particularly at scale. Like 1 billion ball stick balls is not terribly useful. So how do I visualize that stuff? And there are incredible human-computer interaction challenges happening up there. So sport for choice, really. There's a lot of CS going on, and no perceivable end to it, but it's all tremendously exciting stuff.
Might make it into your third edition, maybe? Maybe. I mean, I think that was more of a kind of, hey, come and work at Neo4j pitch than it was a pitch for a third edition. But I think some of that we have to cover, right? Because it really is now where the kind of contemporary graph database community is at. Yeah. Thanks so much. I think, it's been awesome as always to chat with you.
It's been lovely chatting with you again, and stay safe. And I'll catch you on the other side of this zombie pandemic in person.
Indeed, indeed.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech for lots more content from the brightest minds in software development.